So we're looking today at section 6.2, part 1. 6.2 covers sum identities, difference identities, and double angle identities. We're going to do the sum and difference identities today. Then we will do the double angle identities tomorrow. And then we're going to put it all together on Wednesday and look at proving identities. And we're going to have, for resources for proving identities, the quotient identities, the reciprocal identities, the Pythagorean identities, and all of these new identities we're going to learn about in the next couple of days. So we're solving problems today involving what we call the sum and difference identities for sine, for cosine, and for tangent. You know, if times were different, maybe if we had more time, and if it were in the curriculum, I would demonstrate to you where these things come from. But students are not expected to know that. You're not expected to know why these things are true. Sine of, I'm going to say alpha plus beta. Sometimes I will say A plus B. That little fishy looking symbol is the Greek letter alpha, and the one that looks like a capital B is the Greek letter beta. They're the first two letters of the Greek alphabet. Sine of the sum of two angles is the sine of the first angle multiplied by the cosine of the second plus the cosine of the first times the sine of the second. What does this mean? You know, you may look at it and go, big deal, but there are uses for it. What I'm about to show you is not really a use, it's just a demonstration of an example where it's true. If I said to you, take the sine of 21 degrees plus 9 degrees, well, we could use this identity. I could say this is the sine of 21 degrees times the cosine of 9 degrees plus the cosine of 21 degrees times the sine of 9 degrees. Okay. Now, I want to point something out to you, that any of these four trigonometric ratios on the right happen to be irrational numbers. What do I mean by that? I mean, if I take in my calculator, put my calculator in degrees, and I take sine of 21 degrees, I get this weird awkward decimal that it cannot be converted to a fraction. It's an irrational number. It's got square roots embedded in it somehow. And the same with cosine of 9 and all the other ones. But if I put this all together, sine of 21 times cos of 9 plus cos of 21 times sine of 9, an interesting thing happens. I get a rational number. I get 0.5. That's not the point of what I'm doing. I'm just pointing out to you that that's what we would expect to get, because 21 plus 9 is 30, and the sine of 30 degrees is the y-coordinate on the unit circle at 30 degrees, which is 1/2. Okay, so that's what that identity means. We have a difference identity, which you would expect to be very similar to the sum identity for sine. It's sine of A minus B equals sine A cos B minus cos A sine B. And then we have the sum identity for cosine, which is decidedly different. Like, it's structured different. First of all, a cosine sum or difference identity has two terms, and each of the terms are cos, cos, and sine, sine. In this particular case, cos of A plus B is cos A cos B minus sine A sine B. It's not a mistake. It's A plus B in the identity on the left, but then you subtract the terms on the right. And then we have this identity as well. Cos of A minus B is cos A cos B plus sine A sine B. And I would say that you don't have to be overwhelmed by this because they're on your formula sheet and you can always refer to them. But I would also say that over time, you will recognize these. You will go, oh, that's the cos of A plus B. Okay, you will get used to it. I don't know. I've been teaching these identities for years and years. I still don't get used to these. I don't, because the double identity angles for tangent are kind of similar looking, and that's not what we're talking about. The tangent ones, I always need to look on a formula sheet. I'm not even going to bother reading them out to you because I'd have to just look at it and read it piece by piece. It's not something that I've remembered. So we're going to take a look today at some examples that make a use of one of these identities, depending on the situation. The first example is really just a warm-up. It's about recognizing which identity we want to use. So I want you to look at your formula sheet. Locate these sum and difference identities on your formula sheet right now, just so you were aware of where they are. Well, they're below the Pythagorean identities. And there's 6 of them. And then there's also going to be double angle identities that we'll look at. So which of these identities that you're looking at on your formula sheet matches this in pattern? Well, I just look at this and I go sine times cosine. That's got to be the sine of the sum or the difference of angles. And because it's minus, it's this identity. It's sine of A minus B is equal to sine A cos B minus cos A sine B. And it's okay to use alpha and beta. It's okay to use A and B. You feel free to use whatever letters you want. So all this means is that this will be the sine of whatever 42 degrees minus 19 degrees is. This is not an exam question. You're not going to be asked, what is this equal to? This is just warming up to recognizing what these things look like. So this is going to be the same as sine of, I want to say 23. 42 minus 19. Sine of 23 degrees. Which we don't have any way of calculating because that's an angle that, although would be on the unit circle, we're not aware of the coordinates of that point. Okay, so we're done. Any questions with 1A? All right, B. Well, as soon as I see cos times cos and then a sine times sine, I know I'm dealing with a sum or difference identity for either cosine or sine. And the identity that we're going to be looking at here is cosine of A plus B is equal to cosine A cosine B minus sine A sine B. And all that means is that this is going to be equal to the cosine of 2 pi over 3 plus 1 pi over 3. Does that make sense, what I'm doing here? Okay. So what is that equal to? That's equal to cosine of pi. And in this particular case, we can certainly do this. So pi is 180 degrees. When you look on your unit circle at 180 degrees, the x coordinate is -1. So this is certainly now a demonstration of why using identities can make your life easier, particularly if you go on and take calculus next semester. Because finding the value of this, although it can be done, is more work than finding the value of cosine of pi. Similarly, or along the same lines, if it wasn't 2 pi over 3 and pi over 3, if it was this, and this is merely, I'm thinking calculus here. I'm thinking of the work we do in calculus. And I'm doing this to try to give you a reason why this is a valuable tool. If this comes about as one part of a step in a calculus problem, you do not want to carry this disaster all the way through in your other steps. Instead, what you can do is use cosine of 7x. And it's a nice tidy package that carries all of this information with it. It just doesn't explicitly say what all of that information is. And one final one in this, oh no, we didn't do tangent. Okay. Number 2. Now this is a very specific skill or type of problem that you would see on an exam. What is the exact value for sine of 165 degrees? Normally when you see these questions, everybody, you're looking on the unit circle. So if I said, what is the exact value of sine of, I don't know, 315 degrees, you can figure that out because 315 degrees leads you to a point on the unit circle whose coordinates you know. I think 315 is 45 degrees shy of 360. So what that means is, and this is not the question, okay? I'm just pointing out how we solve this type of problem. What that means is that you would be looking on the unit circle at this point, which has coordinates of root 2 over 2, comma, negative root 2 over 2. And since it's sine, just make sure you understand this. I'm sure you do. That's 315 degrees. Are you with me? Okay. So then you would say, since it's the sine of that angle, I'm looking at the y coordinate because that's the way things work. So this would be equal to negative root 2 over 2. Or 1 over root 2, if that strikes your fancy. Doesn't matter. They're the same number. The issue here is, where is 165 degrees on the unit circle? It will lead to a point on the unit circle. You just don't know the coordinates of that point. So this strategy falls apart. We do happen to know the coordinates at 150 and at 180, but not at 165. Well, that's okay. We're going to rewrite this as the sum or the difference of 165. We're going to not take the sine of 165. Let's take the sine of the sum of two angles whose coordinates we do know on the unit circle. And the fact that this ends in a 5 is a clue that one of those angles has to be 45. So as soon as you see that, you go, oh, it's 120 plus 45. Now, could you, I have to think carefully about this. Could you find other combinations here? For example, what is 360 minus 165? Can you figure that out for me, please? 360 minus 165. 185? 195? So 190, that wouldn't work because you don't know the coordinates of 195. So, but there might be other combinations. Okay, it doesn't have to be these particular numbers. It can be any two numbers that add or subtract to give that. And the point is, now we can write this as sine of 120 degrees times cosine of 45 degrees plus cosine of 120 degrees times sine of 45 degrees. And all four of these trigonometric ratios are accessible to us as exact values because those angles are known positions on the unit circle, very specific knowledge about the x and y coordinates. So I would recommend the following. Well, you do whatever you need to do here, but I would recommend doing these two separately if you're going to look on paper. That point on the left is at 120 degrees, and this point is at 45 degrees. So what are the coordinates here? Root 2 over 2, comma, root 2 over 2. And here, negative 1/2, root 3 over 2. That's a 3 in there. Do you get where we're going with this? That sine of 120 degrees is going to be the y coordinate at 120 degrees, which is root 3 over 2. Cosine of 45 degrees is the x coordinate at 45 degrees, which is root 2 over 2. And then plus cos of 120 is the x coordinate at 120, which is negative 1 over 2. And then times sine of 45, which is root 2 over 2, because that's the y coordinate at 45 degrees. Incidentally, I'm going to pause here. Do you remember when I said, what is the exact value of sine of 315 degrees? I didn't If I did explain what I'm about to tell you in the previous unit, I let it slip by accident. You didn't need to know your unit circle that well to know what this is equal to, because you can take in your calculator sine of 315 degrees and get that number and maybe recognize 0.707 as root 2 over 2. Right? I didn't point that out to you. And root 3 over 2 is 0.866 something. Like, you can recognize these numbers. Keep that in mind as we finish this problem. This becomes root 6 over 4 minus root 2 over 4. A very common mistake here, everybody, is to forget to multiply the two 2's together. I think you're kind of thinking maybe, oh, the common denominator is 2. But you're multiplying those two fractions. So we end up with root 6 minus root 2 all over 4. So the simple fact of the matter is, this was 165 degrees, yes? If you take the sine of 165 degrees and you recognize that as root 6 minus root 2 over 4, good for you. But I don't know how you would recognize that. If you do calculate root 6 minus root 2, and divide by 4, you get the same number, but there's no way of unwrapping that and turning that decimal number into the exact value. And these questions may be presented to you as sine of 165 is root A minus root B over C. And if you have the tenacity to start putting in random numbers for A, B, and C until you get that 0.25 whatever, I applaud you. But it's going to be a long journey. Any questions with number 2? All right. Let's take a look at 2b, tan of 7 pi over 12. So although radians are very useful in finding locations, I can't, in my head, come up with 2 radian angles that add or subtract to give 7 pi over 12. So I need to work in degrees here. So I'm going to figure out how many degrees that is. It's 7 times 180 degrees over 12. I want to say it's 105, but is that what it is? It's 105 degrees. So even if this is a written response question, I don't think there's any issue with you saying, radians, no thank you. I'm going to work in degrees. Because the tan of 7 pi over 12 radians is the same as the tan of 105 degrees. Now we have to find 2 angles that add or subtract to give 105. And those angles have to be angles that we have the coordinates of their intersection with the unit circle in our head. It ends in a 5, so it's 45 and 60. It'll always end in a 5. One of the numbers will always be 45, okay? Or if you want to be fancy, 135. For example, could you do that? Sure. 135 happens to be an angle whose intersection point with the unit circle you're familiar with, and so does 30 degrees. But why make your job more difficult? Just go 60 and 45. See, and this is going to illustrate my point that I made earlier. If it's sine or cosine of A plus B or A minus B, I know those. I don't know what this is. I don't know. I want to say 2 tan A tan B on the top. Look at your sum or difference identity for tangent, and it's going to be the sum, and tell me what's on the top. Abby, can you help me out?
Tan A plus tan B.
See, and I'm mixing up the double angle identity with this one. Tan A plus tan B over 1 plus minus tan A tan B. Okay. Okay, so tan alpha plus beta is tan alpha plus tan beta over 1 minus tan alpha tan beta. So what this is going to be equal to is tangent of 60 degrees plus tangent of 45 degrees over 1 minus the product of tangent of 60 degrees and tangent of 45 degrees. And I would highly recommend, since it's tangent, finding these two trig ratios, tangent of 45 and tangent of 60, finding them off on the side. I mean, I happen to know that tangent of 45 degrees is 1, but the reason I know that is ultimately it comes down to the unit circle and saying that at 45 degrees the x and y coordinates are the same and tangent is y over x. Since tangent is not just x or just y, it's y over x, that's why I think you need to very clearly, in your head, figure out what they are first before you proceed. And when I take a look at tangent of 60 degrees, well, I happen to know it's root 3, and maybe I've accidentally memorized that. But what I'm looking at here now is the following. At 60 degrees, the coordinates are 1/2, comma, root 3 over 2. And I will leave it to you to write, if you want, root 3 over 2 over 1 over 2 and simplify that, you'll get root 3. Capiche? Okay. So what turns out to be an easy problem doesn't present itself as an easy problem. This looked complicated because the tangent identities are always more complicated. It's not. This will be root 3 plus 1 over 1 minus root 3 times 1. Which is, I'm going to write it this way, 1 plus root 3 over 1 minus root 3. Just because I like the symmetry of that rather than saying root 3 plus 1 on the top, I've just changed the order of those. Which means it could have been that the question was framed this way. I mean, I could have gone a full A, B, C, D thing there, but whoops. You know what? D is okay here, but I think I would, not to intentionally mess with you, but I wouldn't lead you to the idea that those two numbers are going to be the same. I'm getting in the habit lately of putting one of these numbers that way because, I don't know, these two are the same. If I multiply the top by 2, which is root 4, I can get a slightly different set of numbers. So I'm giving you the fact that this is a 1 to lead you to that idea, that it's simplified. And you're not allowed to use larger numbers. Does anybody have any questions with that example? Okay. Simplify. Another, I don't always want to bring it back to calculus, but another situation where in calculus you might be setting up a problem, an optimization problem or whatever, and in your journey you have to use this result. In a whole bunch of other stuff, it's there. Well, if you can simplify that first, you probably should. Let's see what happens when we simplify this. Well, how do we simplify this? We use the difference identity for cosine. the difference identity for cosine, and this is not pronounced properly, I'm just in a teaching mode right now. Cosine of a difference is cos plus sine sine. It's cos A, cos B, plus sine A, sine B. But that's the idea. And this is really, really simple now, which is good because we're asked to simplify it. This is 0. Cos of pi over 2 is nothing because pi over 2 is 90 degrees and the x-coordinate at 90 degrees is 0. This is 1. So what this is equal to is sine of x. Because we're going to have 0 times cosine of x plus 1 times sine of x, but 0 times cosine is 0. B, tan of pi plus x. I think I got it. Tan of pi plus x will be tan of pi plus tan of x over 1 minus tan of pi tan of x. So I'm applying the sum identity for tangent. Now all I have to do is say, what is the tangent of pi? Well, the tangent of pi is 0. Because on the unit circle, the coordinates at pi radians are -1 comma 0, and tangent is y over x, so you get 0 over -1, which is 0. Well, that means that this is equal to tan of x. Well, I'll put in the zeros. 0 plus tan of x over 1 minus 0 times tan of x. Who knew that this is equal to tan of x? Well, you do now, but only because of this identity. The bottom of this expression has the 1 plus, or minus rather, 0 tan x. 0 tan x is nothing. You don't need to write it. So we're left with tan x on the top and 1 on the bottom, which is tan x. Any questions with that example? All right, we have one more. And you know, this question in particular, as well as the previous two, are all about building those algebra muscles in your brain. Cosine of angle x, actually there's one more example after that, isn't there? Cosine of angle x is 5 over 13, where angle x is in quadrant 4, and tangent of angle y is 4/3, where angle y is in quadrant 3. Why do I keep saying angle x? Because this question has x's occurring in multiple places. This x is a rotation angle that is in quadrant 4, whereas when you take a look at this point in quadrant 4, this x is not a rotation angle. What that x is a coordinate. Are you with me on that? And I've grappled in the past with me changing the capital X to A and the capital Y to B, but then sooner or later you see it on an exam and students get confused. Can you just double check something though? Is your Y capitalized in this table? Okay, good. I'm just going to fix it for next time. So give me a second. So we want to be careful with all of the x's and y's. We'll come back to those tables in a second, but let's apply the sum identity for sine to sine of x plus y. We're going to get sine of x, cos of y, plus cos of x, sine of y. So how are we going to find these four trigonometric ratios? Well, this is a y over r. But it's y over r for angle x. Angle x terminates in quadrant, what did we say? Quadrant 4, down here someplace. There is an x and a y coordinate pair down there, and there's a value of r down there. The sine of that rotation angle x will be y over r. The cosine of y will be x over r. But it's going to be x over r for angle y, because it's cosine of y. Do you see the need to be very organized and clear in your thought here? So this x is this x. This r is this r, because it's for angle y. On the other hand, this y is this y, and this r is this r, because it's for angle x. And if you feel totally at ease with that, I don't. I get confused by that, and it makes me tense to have to sort through all of this. So if you feel tense in having to sort through all of this, in other words, a little bit confused, that's normal. Over here, this piece, since it's cosine, it will be an x over r. Since it's angle x, these are going to be blue. So I'm associating everything here with blue in what I've done. Angle x, anything associated with angle x is blue. And then over here we're going to have, this will be a y over r. Why is this a y over r? Is it because there's a y in sine of y? No, it's because there's a sine in sine of y. Oops. There we go. And angle y is all of the yellow stuff. So now we go back to the previous unit. You have to find x, y, and r for both of these angles. When we take a look at angle x, cosine of angle x is 5 over 13. Well, the only thing that makes sense is r is 13 and x is 5. R has to be positive no matter what. If cosine is positive, x has to be positive. And by the way, it's in quadrant 4 where x is positive. So I'm glad to see some of you grabbing your calculator here. I'm not going to show this work. I think it's a fairly straightforward calculation, and I've not chosen any radicals in any of this. I believe for y squared, you're going to get 144. Am I right? So you take the square root and you get 12, but you need to put negative 12, because in quadrant 4, y is negative. Okay. Over here, for angle y, tangent is 4/3, which means y is negative 4 and x is negative 3 because it's in quadrant 3. So those negatives are hidden from you. And that means we calculate r. I think most of you know that if you have a 3-4 combination for x and y, r is 5. So what do we get? We get sine of x is negative 12 over 13. Multiplied by cos of y is negative 3 over 5. Plus cos of x is 5 over 13. Times sine of y is negative 4 over 5. I would always double check things here. Like meaning I would. I'm not saying you should, although I am saying that too. Negative 12/13, negative 3/5, 5/13. Good, we're okay. So these are both going to be fractions over 65. And I get 36 minus 20. So I get 16/65. Are we okay with that? All right. What about cotangent of x plus y? Okay, well, this is ramping it up a notch. There are two ways that you can do this, two kind of general approaches. I would say, well, first of all, with my approach, I cannot forget that that's what I'm after. And the reason why I'm really highlighting it in my brain is that I don't have an identity for cotangent, so I'm going to find the tangent of x plus y. And then after all my work, I'm going to take it and take the reciprocal of it to get cotangent. There's another way you can do it, but this is just what I prefer. This is tan of x plus tan of y over 1 minus tan of x tan of y. This is the third time today we've used this identity. I'm pretty sure I have it right. Okay, good. So now I need to look at these numbers, right? Like, what is tan of x? Well, tan of x is y over x for angle x. Tan of x is going to be negative 12 over 5. So this is a y over x, but we're focusing on angle x. This will be y over x, but we're focusing on angle y. Well, we already know that. It's 4/3, isn't it? Weren't you told outright in the question that the tangent of y was 4/3? Is that correct? Okay. And then on the bottom, I'm going to have 1 minus the product of these. And I think there comes a time where, particularly with numbers, you don't have to worry about simplifying this. Use your calculator. Figure out what the numerator is equal to and write it down. Figure out what the denominator is equal to and write it down. Divide them and convert it to a fraction, and we will have our answer. I would, and maybe it's just the product of my education, I would really shy away from trying to enter that all at once in your calculator. I think you're asking for trouble. So I would find this by taking negative 12 divided by 5 and adding 4 over 3. It's that number. I would then take 1 plus, I'm not going to waste my time entering minus a negative. I know this will be plus. 48 over 15, this is just the way my mind works. 12 times 4 is 48. 5 times 3 is 15. This is the denominator. I need to take this number and divide by this number. Negative 16/63. I don't care how you get it at that point in time. Right. We've discovered that tangent of x plus y is this. Negative 16/63. Yeah. So this is negative 63/16. You know, in retrospect, I suppose we could have just flipped this whole thing over from the beginning, couldn't we have? I could have written cotan of x plus y equals, and then just flipped that identity over. 1 minus tan x tan y over tan x plus tan y. Okay, we have one last example to go here. A rotation angle has its terminal arm, and the terminal arm passes through 8, 3. What's the exact value of sine of 2 pi over 3 plus theta? This is now a full-blown diploma exam question. This is something you would expect to see on an exam. What we can do is figure out what this is by using the sum identity for sine So sine of A plus B is sine of A cos of B plus cos of A sine of B. for these two, you can use the unit circle. And don't psych yourself out and go, well, 8 comma 3 doesn't pass through the unit circle. No, it doesn't. But a radius of 1 will, and we can use the unit circle to find sine of 2 pi over 3 or cos of 2 pi over 3. In fact, give this some thought just for a second here. And see if you can confirm that sine of 2 pi over 3 is root 3 over 2, whereas cos of 2 pi over 3 is negative 1/2. Yes? Okay. How are we going to find these? We're going to use the XYR thing for angle theta, where we know that x is, I think, 8. Yep. X is 8. Y is 3. As an exact value, what is r? We need to know r because there's an r in the cos theta and the sine theta. Root 73. I'm just going x squared plus y squared equals r squared. 8 squared plus 3 squared is 73. So r is root 73. So cosine of theta is the x coordinate at theta divided by the r value. Sine of theta is the y coordinate at theta over the r value. There's multiplication signs in here. So this is our answer. This is all we have to do. I get 8 root 3 minus 3, and this is all over 2 root 73.